Electromagnetism Part 1 Magnetic field around a straight conductor carrying current and a coil. Is it that magnetic fields are formed only around magnets? No, we can observe magnetic fields around current-carrying conductors also. Let us show the magnetic property of current-carrying conductors by an experiment. Place a pivoted magnetic needle on a table. Hold a straight copper wire just above the magnetic needle and parallel to it. When an electric current is passed from a battery through the copper wire for a short time, it can be observed that the magnetic needle is deflected in one direction. The deflection of the magnetic needle is because of the interaction between the magnetic field produced around the current-carrying conductor and that of the magnetic needle. This proves that the magnetic field is developed around a conductor when an electric current passes through it. When the electric current is stopped, the needle comes back to its original position and there will be no deflection. That is, the magnetic field is temporary. Now let us reverse the battery to reverse the current in the circuit. The needle deflects in the opposite direction when the current is reversed. What do you understand from this? Reversing the current reverses the magnetic field also. Direction of electric current. Electric current flows from the positive terminal of a battery to the negative terminal. Let us find out the direction of the magnetic field due to current passing through a conductor. Make a hole on a smooth cardboard and support it horizontally on two wooden plugs. Insert a straight copper wire perpendicular to the board through the hole and connect its ends to a battery. Scatter fine iron filings on the cardboard and tap the card gently. Observe the distribution of iron filings. Distribution of iron filings is not uniform in all circles. They are crowded near the wire. Iron filings are arranged thickly near the wire, but they become more and more thin away from the wire. Here the conclusion is that the shape of the magnetic flux lines is circular around a straight current-carrying wire. The flux density is greater very near the wire, but as the distance from the wire increases, the flux density is found to be decreased. Place a magnetic needle on the cardboard. Now pass electric current through the conductor. Mark on the paper the position of the north pole of the magnetic needle. Shift it so that now the south pole of the magnetic needle is at the marked point. Mark again the position of the north pole and continue the activity. Keep the magnetic needle at various points on the cardboard and repeat the experiment. Remove the magnetic needle and draw a curve joining the successive points you have marked. See the shape of the curve obtained. All the curves are circular in shape. Repeat the experiment by reversing the direction of current. There is a relationship between the direction of the current and that of the resulting magnetic field. As the direction of the current changes, the direction of the magnetic field also changes. In the pattern of the iron filings, the flux lines are concentric with the wires as their center. We can repeat this experiment with scattering iron filings on the cardboard. Adjust the rheostat to increase the current in the circuit. The change is that the iron filings are crowded more thickly than before. That is, the flux density is increased. The inference here is that the intensity of magnetic field around a current-carrying conductor increases as the strength of current through the conductor increases. Fill a trough with water. Arrange a bar magnet at the center of the surface of water in the trough. Magnetize a needle and identify its poles and pass the needle through a piece of thermocol. Place this thermocol piece on the water surface in such a way that the north pole of the needle comes near the north pole of the magnet. We can see that when like poles come together, they repel each other, and unlike poles come together, they attract. Thus, when north pole of the needle comes near the north pole of the magnet, they will repel each other. Likewise, when north pole of the needle comes near the south pole of the magnet, they will attract each other. The direction of the magnetic line of force. The direction of the magnetic line of force at a point in a magnetic field is the direction of motion of a free isolated north pole placed at the point. The direction of line of force is the direction of the magnetic field at that point. We can repeat the experiment by reversing the current. Compare the directions of the current and the magnetic field in each case. There is a relationship between the direction of the current and that of the resulting magnetic field. As the direction of the current changes, the direction of the magnetic field also changes. This relationship can be found out by using the thumb and other fingers of your right hand. Imagine that you are grasping the current-carrying conductor in your right hand such that the thumb indicates the direction of the current, then the direction in which the ends of other fingers point indicates the direction of the magnetic field. This is the right hand rule. The magnetic field around a circular coil. Pass a copper wire through two holes in a cardboard and bend it in the form of a circle. Connect it to the terminals of a battery through a switch. Scatter iron filings on the cardboard around the coil. Switch on the current and gently tap the cardboard. There is peculiarity when we observe the distribution of the iron filings when compared to that around a straight conductor. The iron filings are arranged in the form of circles around the wires in both places where the wires pass through the cardboard. The iron filings are distributed in the form of circles near the wires. The curvature of the flux lines decreases as the distance from the wire increases. Moreover, they become more and thinner as the distance from the wire increases. As the center of the circular wire, the curvature disappears and the flux line appears as a straight line. Conclusion here is that a circular coil of wire behaves like a magnet with a north pole at one side and a south pole on the other side. We can see what happens if the number of turns of the coil is increased. More iron filings are thickly arranged around the wire. That is, the flux density is increased when the number of turns of the coil is increased. In this activity, we can mark points A and C on the cardboard outside the circular coil and B inside. All the points should be in a straight line. Keep a magnetic needle on each of these points and switch on the current. The observation is that the needles are arranged so that their ends point in different directions. The needle at B is arranged so that its axis is perpendicular to the plane of the coil. The direction of the north pole of the magnetic needle is different at A, B and C. We can draw a line on the cardboard through B perpendicular to the line ABC. Keep magnetic needles on various points on this line and repeat these experiments. There is no change in the direction of the magnetic needle when the needles are placed at different points on the line. The axis of the needle coincides with this line at all points on the line. This is because the flux line through the center of the coil passes through this line. Conclusion is that the flux line passing through the center of the coil is a straight line. This line is perpendicular to the plane of the coil. The direction of the lines of force depends on the direction of the flow of current through the coil. Make 2 turns of the same wire in circles, not touching each other, and repeat the experiments. Let us see the direction of the magnetic field around each coil. Very near to the coil, circular flux lines are formed around each coil. Part 2. Solenoid. Is it possible to lift heavy objects by a crane? Cranes are capable of lifting heavy objects. The reason is explained through a simple experiment. We can explain the working of a crane by a simple experiment. Take a thin piece of iron and some iron filings. Connect a battery to the 2 ends of the piece. When we turn on the battery, we can see that the iron filings get attracted to the iron piece. When we disconnect the battery, the iron filings are dropped from the piece of iron. This shows that when current is passed to the piece of iron, it attracts the small iron filings. When the battery is turned off, no current flows through the iron piece. A solenoid is a coil wound into a tightly packed helix. Make a solenoid by winding the copper wire around a small pipe. Remove the pipe and the solenoid for doing the experiments. Connect the ends of the solenoid to a circuit containing rheostat, a switch and a battery. Switch on the circuit. Move a magnetic compass box both inside and outside the solenoid and mark the points indicated by the north pole of the needle. Join these points and draw the magnetic lines of force with the direction marked. The direction of the magnetic field inside the solenoid is the same. Let us make a solenoid by winding 25 turns of insulated copper wire on a small piece of PVC pipe. Keep a magnetic compass needle at one of the free ends of the solenoid. Now pass current through the solenoid. When current passes through the solenoid, the compass needle shows a deflection in it. If we increase the number of turns, there will be an increase in the deflection of the compass needle. We can repeat the experiment by inserting pieces of iron binding wires or soft iron core into the solenoid. When we increase the number of iron binding wires in the solenoid, the deflection of the needle will be again increased. The strength of magnetic field increases with increase in the binding wires. The strength of magnetic field increases with the increase in the number of binding wire and the increase in area of cross-section of the core. We can repeat the experiment with varying the current in the solenoid. The needle deflects more when the strength of current through the solenoid is increased. That is, the magnetic field increases with the increase in the strength of the current. Factors that influence the magnetic field are strength of current, number of turns, and the area of cross-section of the iron core. The magnetic field is created because of the movement of electrons through the conductor. Usually, this magnetic field is so small that it is unnoticed. This can be increased by increasing the current flow or by forming the conductor into a coil. If a soft iron bar is placed in the field of a current-carrying coil, the bar will be magnetized and will be drawn towards the center of the coil, thus becoming the core of an electromagnet. The magnetic field around a solenoid. A long insulated conducting wire wound in the form of a helix is a solenoid. Make a solenoid by winding the wire through the holes. Remove the pipes. The solenoid is ready for doing the experiment. Connect the ends of the solenoid to a circuit containing a rheostat, a switch, and a battery. Switch on the circuit. Move a magnetic compass box both inside and outside the solenoid and mark the points indicated by the north pole of the needle. Join these points and draw the magnetic lines of force with the directions marked. The direction of the magnetic field inside the solenoid is the same. Making groove in a cardboard with paper pasted on it, we can repeat the magnetic field experiments. Polarity. One end of the solenoid shows the presence of a north pole and the other end a south pole. The north pole of the magnetic needle is attracted to the end of the solenoid where the south pole is formed. The polarity of this end of the solenoid is south pole. A north pole is formed at the end of the solenoid. The flow of current through a solenoid is from the positive terminal of the battery to the negative terminal. The direction of the current through the solenoid can be compared to the motion of the hands of a clock. If the current that enters the solenoid from the wire connected to the positive terminal of the battery is similar to the motion of the hands of a clock, it can be clockwise direction. If it is clockwise, the polarity formed at this end is south pole, and if it is anti-clockwise, it is north pole. We can repeat the experiment by reversing the current through the solenoid in the circuit. Let us see the magnetic field around a bar magnet and a current-carrying solenoid. A current-carrying solenoid behaves like a bar magnet. It is not practically possible to draw the flux lines through the interior of a bar magnet, but it is possible to draw the flux lines through the interior of a solenoid. The strength of a bar magnet is limited, but the magnetic power of a solenoid can be increased or decreased. A solenoid carrying current behaves like a bar magnet. Electromagnets are used in the situations like electric bell, electromagnetic relay, maglev train developed in Japan, electric crane, MCB, that is miniature circuit breaker, and ELCB, that is earth leakage circuit breaker. Connect a solenoid through a switch to a battery. Place a soft iron core inside the solenoid. Keep one end of the core of the solenoid in contact with iron filings. Switch on the current. When the circuit is switched on, the core becomes an electromagnet. Then it attracts the iron filings towards it. When the current is switched off, the power of the electromagnet is lost. Hence, the iron filings fall down from the core. The force of attraction and repulsion between two magnetic poles increases with the increase of power of poles and decreases with the increase in distance between the poles. Spread some iron filings on a glass sheet. Place two magnets on it without contact and with their unlike poles face to face. Let us mark the formation of flux lines between the poles. Let us also mark the flux lines if the magnets were kept with their like poles facing each other. The ends of the magnet where the magnet shows strong magnetic properties are called poles of the magnet. A magnet has two poles, namely North Pole and South Pole. A coil of wire wound in the form of a spring is called a solenoid. Let us see how an electromagnet is made. Insulated copper wire is wound from one end of a soft iron core to the other end several times. A direct current is sent through the wire. The core becomes a magnet. But when the current is switched off, the core does not show any magnetic properties. This arrangement is called an electromagnet. It functions as a magnet only when the current flows through the solenoid. When the current is passed through the conductor used in cranes, a magnetic field is produced. Electromagnetism is responsible for practically all the phenomena encountered in our daily life, with the exception of gravity. There are so many instruments we encounter in our daily life works according to the law of electromagnetism. Some of the examples are fan, motor, generator, radio, dynamo, microphone, loudspeaker, fluorescent lamp, etc. Cranes are capable of lifting several tons of iron, steel, or other heavy objects. This is achieved by using very powerful electromagnets. Electromagnets in various forms are very useful and become unavoidable in our daily lives. Some applications of electromagnets are electric bell, electromagnetic relay, electric crane, MCB or miniature circuit breaker, maglev train that is developed in Japan, ELCB or earth leakage circuit breaker. Part 3. Electric bell. How is an electric bell strike to and fro continuously? Let us find out. Electric bell is a device in which electromagnet is used. Parts of an electric bell are hammer, strip with spring action, automatic make and break arrangement, iron core, screw, iron strip, coil of wire, and gong. Working of an electric bell. When the current is switched on, electricity is passed through the wire wound around a soft iron core. The soft iron core is magnetized and it attracts the iron strip. The hammer filtered with soft iron strip hits the bell and sound is produced. When the iron strip is attached to the electromagnet, the circuit breaks due to the gap developed between the core and the screw. When the circuit breaks, the core loses its magnetic properties. The iron strip again comes into contact with the screw and the circuit is completed. The core again becomes a magnet. This process continues and the bell works. Experiment with electric bells. An electric bell is a mechanical bell that functions by means of an electromagnet. When an electric current is applied, it produces a repetitive buzzing or clanging sound. Electric bells have been widely used in telephones, fire and burglar alarms, as school bells, doorbells, and alarms in industrial plants, but they are now being widely replaced by electronic sounders. Electric bells are the practical and most common application of electromagnetism, which have now become inevitable to every household. When compared to permanent magnets, electromagnets are generally stronger. That is why electromagnets are used in power generators. The ability to control the timing and intensity of magnetic field has led to the incorporation of electromagnets in almost all aspects of our daily life. Electric motors, relays, speakers, disk drives all depend upon the accuracy and consistency provided by the electromagnets. Almost all electromagnets are based on the simple basic design: an electric current through a coil and a soft iron core. James Clerk Maxwell was a Scottish physicist and mathematician. His most prominent achievement was formulating classical electromagnetic theory. This united all previously unrelated observations, experiments, and equations of electricity, magnetism, and even optics into a consistent theory. Maxwell's equations demonstrated that electricity, magnetism, and even light are all manifestations of the same phenomenon, namely the electromagnetic field. His work in producing a unified model of electromagnetism is one of the greatest advances in physics. Michael Faraday built two devices to produce what he called electromagnetic rotation, that is, a continuous circular motion from the circular magnetic force around a wire. 10 years later, in 1831, he began his great series of experiments in which he discovered electromagnetic induction. These experiments form the basis of modern electromagnetic technology. Electromagnetism is one of the four fundamental interactions of nature. The other three are the strong interaction, the weak interaction, and gravitation. Faraday showed that a magnet could induce an electric current in a wire. Thus, he was able to convert mechanical energy into electrical energy and discover the first dynamo. Electromagnetism manifests as both electric fields and magnetic fields. Originally, electricity and magnetism were thought of as two separate forces. This view changed, however, with the publication of James Clerk Maxwell's 1873 treatise on electricity and magnetism, in which the interactions of positive and negative charges were shown to be regulated by one force. In 1819, Hans Christian Ørsted found out that there is a magnetic field around a straight current carrying conductor.